In this lecture, we will discuss about the Laplace transform with few problems and some basic definitions. Laplace transform is a powerful integral transform that converts a function of time f of t into a complex frequency domain function f of s, where s plane is equals to the real part sigma and the imaginary part omega. It effectively turning complex linear ordinary differential equations into simpler algebraic equations. Mathematically, we can write Laplace transform of a time domain function is equals to integral where the upper limit is infinity and the lower limit is 0 f of t e raised to minus st dt. Key reasons for using Laplace transform: it simplifies differential equations, so it turns complex differential equations into algebraic equations which are much easier to solve. Handles initial conditions. Unlike other methods, the Laplace transform incorporates initial conditions directly into the algebraic expression, enabling the determination of the total system response. Analyzes system dynamics. It converts time domain signal like impulse responses into the S domain, where system stability and behavior can be easily analyzed by studying poles. Convolution to multiplication. It transforms complex convolution integral in the time domain into simple multiplication in the S domain. Broad applications. It is crucial in electrical circuit analysis, control system, PID controllers, digital signal processing, and modeling physical systems, for example, mass spring damper. Let's consider an LTI system with input x of t and output y of t, where h of t is the impulse response. Like x of t is given to an LTI system whose impulse response is h of t, and the output is the convolution of the input and the impulse response. So we consider the complex exponential signal as our input signal x of t, which is equals to g e raised to power st, where s is equals to sigma plus j omega complex form, but for Fourier transform we only consider omega, so that is one difference that we consider S domain for LT, like for the Laplace transform, so that is real and imaginary, where sigma is real of S plane and omega is the imaginary part of the S plane. Now next we will drive the equation for the Laplace transform. Output of LTI system, as is given from this black diagram, is y of t is equals to the convolution of h of t with the x of t, or you can write y of t is equals to integral with the lower limit minus infinity, upper limit is infinity, h of tau x of t minus tau d tau. So y of t is equals to the integral h of tau x t minus tau d tau. So y of t is equals to the integral h of tau, and we know the input x of t is equals to g e raised to power s t minus tau d tau. So gst is a constant, we can take it out, g e raised to power st h of tau e raised to power minus s tau d tau. And we know g e raised to power st is the input, so we can write x of t in place of g e raised to power s of t, and then we can say that okay, y of t is equals to x of t, which is our input, integral from minus infinity to infinity, h of tau e raised to power minus s tau d tau, where this is basically the impulse response in frequency domain, or you can say in S domain. So x of t h of s multiplied by, from this equation we can rederive h of s, which is equals to the Laplace transform of h of tau, that is equals to the integral of h of tau e raised to power minus s tau d tau. Similarly, we can write the Laplace transform of input x of t, so that is x of s is equals to the Laplace transform of x of t, and we are just basically replacing h of tau with x of t e raised to power minus st from e raised to power minus s tau. Like we can write like this. So if it is input, we can write the Laplace transform like this. So that is the basic derivation of the Laplace transform with the given input of an LTI system. Now we can show what is the relationship between the Laplace transform and the Fourier transform. X of s is equals to the Laplace transform of x of t is equals to integral from minus infinity to infinity x of t e raised to power minus st dt. And we know that s is equals to sigma plus j omega. So if we insert that s in this equation, we can rewrite this equation in this format like e raised to power minus sigma plus j omega t dt, or we can separate it because e raised to power minus sigma is multiplied by e raised to power minus j omega. So we can write that equation into two parts, e raised to power minus sigma t multiplied by e raised to power minus j omega t. And we can say that okay, this is our equation number 1. So we can say that okay, x omega is equals to the Fourier transform of x of t, that is equals to the integral of x of t e raised to power minus j omega t dt. So from previous equation, that is equation number 1, so this can be a part of that Fourier transform like this equation. And we can say that okay, f of t is equals to x of t e raised to power minus at integral x of t e raised to power minus at e raised to power minus j omega t. So then using this relation, we can rewrite equation 1. So that is equals to Laplace transform of x of t is equals to x of s. So that is equals to f Fourier transform of x of t e raised to power minus sigma t, because this e raised to power minus at is the additional part. So we can write that as it is. So the Laplace transform of signal equals the Fourier transform of the signal multiplied by e raised to power minus real part. So that is this one. So e raised to power minus real part, so which can be written in s plane x of s. So that is equals to x of omega if we only have the imaginary part. Like if there is no real part, then we can say the Laplace transform is equals to the Fourier transform. But if there is a real part, then we can write in this equation in this format. Now we can see what is the inverse Laplace transform. So if you take the Laplace transform of x, that is equals to x of s, that is equals to Fourier transform x of t e raised to power minus sigma t. So we can write x of t e raised to power minus sigma t. So this Fourier transform will be on the other side, so it becomes inverse Fourier transform. So inverse Fourier transform of x of s, or we know that s is equals to sigma plus j omega, and we know the inverse Fourier transform of x omega, so that is equals to 1 over 2 pi integral x omega e raised to power j omega dt. So using that equation, we can rewrite this equation in this format like x t e raised to power minus sigma t equals to 1 over 2 pi integral x sigma plus j omega e raised to power j omega t d omega. So this is constant, it will be on the other side, and you know the negative power becomes the positive power, and so that is why we can rewrite this equation in this format. So the constant we can take the constant inside the integral, or we can write the constant before the integral, so it will make no difference. So we move that constant e raised to power sigma t inside the integral. So x e raised to power, so x so we can rewrite this equation in this format. Why? Because the basis is same, e raised to power sigma t, e raised to power j omega t. So we can write single base e, and the power is sigma plus j omega. So that is why we can write that equation in this format. And so we want the result in s domain. So s is equals to j plus sigma plus j omega. So and differentiating both side, so because here you see it is d omega, but we want in ds. So we know the equation of s is equals to sigma plus j omega. So differentiating this equation on both side, we will end up with this equation like d of s is equals to d sigma plus j d omega, and we know the derivative of a constant is 0, so that is why we can rewrite this in this format: d omega is equal to 1 over j ds. So we will insert these values in this equation, and we can write a new equation like x of t is equal to 1 over 2 pi x of s e raised to power st ds by j, and this j is a constant. We can take it out from the integration, and we can write the final inverse Laplace transform. So that is equals to x of t is equals to 1 over j 2 pi integral x of s e raised to power st ds. We can solve few problems to have better understanding of the Laplace transform. Determine the signal x of t for which the Laplace transform is given by this equation: x of s is equals to s plus 1 divided by s square plus ts plus 2. So let's solve this transform. We can rewrite this transform in this format, and then we can also write the denominator by taking the factorization, like s square plus 3s plus 2. If you factorize it, so you can write that denominator in this format: s square plus 2s plus s plus 2. And further you can take s common from this equation, and the remaining is s plus 2. And then from this pair you can take 1 common, so you can write s plus 2. And from this two pairs you can take common s plus 2, and then you can write s plus 2. So where s, and then here it is 1, so you can cancel this s plus 1 with this one. The remaining is 1 over s plus 2. And we know if this is the format, we can write this format in time domain: e raised to power minus at ut, and you know a is 2, so that is why you write e raised to power minus 2t ut. Second problem is that determine the signal xt for which the Laplace transform is given by this equation. So similarly, we first try to factorize this denominator, but as you can see, there are no pair. You can't find any pair which can give you the product 10s square and the sum 2s. So that is why you can rewrite this denominator in another format, like you can rewrite that denominator into this format: s square plus 2s plus 1 plus 9. And here you can use that formula: s plus 1 means a plus b whole square. So this is your a, this is your b, and that is 2ab. So you can write s plus 1 whole square, and then this one is 9, so that is 3 square. And then you can write the numerator like in this format: s plus 1 plus 1. And then you can again take the different, like you can write s plus 1 divided by this denominator plus 1 divided by this denominator. Like you can rearrange in the different matters, like you can simplify using different techniques. So this is the easiest technique to simplify this transform. So you can take the inverse Laplace transform, and here so that is the easy to take the inverse Laplace transform of this part. But here you see the on the upper stair there is a 3, so you can rewrite like this equation: e raised to minus at cos omega t ut, if that is the transform: s plus a divided by s plus a square plus omega square. So that is this one. But if so that is the part, then you can write this equation: e raised to minus at sin omega t ut, so that is equals to omega. So s plus a square plus omega square. So on the upstairs we don't have omega here, so this is omega 3, but here we don't have omega, so that is why we write this. So if you see, we don't have omega on the numerator, so that is why we see there is omega 3, so that is why we manipulate this like this: 1 by t 3 multiplied by 3, so 3 will be cancelled with this 3, and the remaining is 1 as well. So we can write in this format, so that one numerator can be written like this: 1 by 3 multiplied by 3. And then these two relations we can use, and we can write the inverse Laplace transform of x of s, so that is x of t is equals to e raised to minus t cos 3t ut plus 1 over 3 e raised to power minus t sin 3t ut. There is another problem that find the inverse Laplace transform of these questions. So this is you can try to solve this inverse Laplace transform. So this is homework assignment for you to solve this as the inverse Laplace transform, and let me know what is the answer so we can further discuss on it. So if you solve that transform, so it will be good. Like you can make it as an assignment and you can take it as an exercise.